The first thing is that I am an associate editor of this journal. If anybody's interested in submitting work, I'm always happy to discuss your ideas. I handle manuscripts for this journal, and we are open access and it's free, basically for people to look at this journal until mid 2027. More info here if you want to take a look at it. Happy to discuss more. All right, now back into my talk, and kind of digging deeper into perovskite solar cells. But before that, I'm going to make a screenshot here of us interacting through the web. So give me a second, just because I want to make sure that later on we're able to show this to people that we're interacting through this meeting. Okay, got it. Cool. So let's move on. The first thing that I want to do is acknowledge my group. This is my group at Georgia Tech, a very diverse group of people from different academic backgrounds and from different parts of the world, who come to Georgia Tech to basically make the research that I'm showing. I'm going to be showing today. Mainly the work of Dr. Juanita Hidalgo, who graduated 2 years ago, and Andres Castro, who graduated a year and a half ago, and some other people who have been in the group for over 6 years. So what are perovskites and why are we interested in them? Perovskite is a crystal structure that has this corner sharing form. And you can see here that in the middle, we have this atom that is surrounded by all these other atoms, and it forms this crystal pattern that basically repeats itself. And that's a perovskite crystal. And first, we have the A side cation, which sits kind of in the middle of those octahedra. It's not forming covalent bonds, but it's forming some electrostatic interactions. And those are normally charged materials, or it could be molecules or atoms that are basically not, that are charge imbalance and compensate with the additional iodine that is here. So you can imagine as an electrostatic interaction, a positive and a negative that interact with each other. In the B side, that's the center of that octahedron. We normally have things like lead or tin or germanium. So heavy metals basically that still sit here. And on the X side, that's the purple atoms here. We have halides, so iodine, bromine, and chlorine. That's why we call these ABX3 halide perovskites, because we have a halide that basically is kind of the bond that keeps this whole structure together. And so halides are very, very important for making sure that the structure is robust and stable. The organic material that is in the center of that octahedron doesn't contribute too much to the density of states or to the electronic properties of the material. Most of the electronic properties are dictated by the lead here on this edge here, and by the iodine here on this edge here. The organics don't really contribute. They're more deep in the density of states, so they don't really contribute. But what they do is that they help us. It's kind of, you can imagine it as the glue of the structure. The organic, or the A side cation, sits in the middle, is charged, and forms negative and positive interactions. And those negative and positive interactions lead to different dimensionalities. For example, here we can have a 0D structure where we have this octahedra that, instead of forming corner sharing, they're kind of isolated. You can see here that we have this isolated group of octahedra, 2 octahedra that are coming together, but they're isolated from the next one. So this is what we call a 0D structure. We can also do some other things that have some degree of corner sharing, like this atom here, and this atom here, and this atom here, but they're not continuously sharing here. So here there's a disconnection between this atom and this other atom. And so that means that we have what we call a 1D structure, where we have a 1D or 2D structure, where we have one of these octahedra sheets connected to another, but separated by an organic material that is very large. So this organic material kind of separates that structure. We can do some other fun things, like, for example, having two sheets. This is one sheet and two sheets. They have the corner sharing, corner sharing, corner sharing, corner sharing, corner sharing, pretty much in all directions until they're separated by this large organic. So the organic kind of serves as a spacer in between the different sheets. And this is what we call an n equals 2 structure, where we have two of the sheets kind of one on top of the other, and then separated by these large organics. So these are 2D structures. We can make them with these types of materials. And then the kind of fruit fly, or the most commonly available perovskite is going to be the 3D perovskite, which has this organic material that is pretty small, sits in the middle, and has this octahedra corner sharing octahedra in all directions. This is why we call this a 3D structure, because everywhere you see there is connection between the octahedra. Even coming out of the computer, you're going to see some of these octahedra kind of interacting with each other. So this is a 3D structure. And why do we care about this, what we call dimensionality? Basically, whether we have corner sharing in all directions or in just one direction, we care about it because it gives us different properties. Here's the emission, and the emission is very important, for example, for absorption of light or emission of light. You can think of your LEDs that you're using right now to light the room. Those are going to be most likely LED if they're modern light fixtures. And you can control the color of light depending on the material properties. So here what we can see is that we can control the colors of the materials that emit that light as a function of dimensionality. So the more 0D and 2D structures give you this blue light or green light, whereas the 3D structures give you more of the yellows and reds. So we can combine these to make materials that make light emitting devices or LEDs. Okay, so now let's dig into the solar cell. The solar cell that we're going to be discussing today, and I'm going to be working a lot on this today in this talk, is based on a perovskite material. The perovskite is this material here. It sits as a part of a sandwich that absorbs light. So what happens is that light comes in, and this is an SEM image. So actually, we've cut the device that we make in the labs, and we can see here how those layers look like. So here's the perovskite layer, about 450 to 500 nanometers thick. So pretty thin. This is about 500 nanometers. And then we have these other layers here that are sandwiching that perovskite that helps us extract the electrons and holes after they're excited by light. So light comes in, and those are photons. And then that energy from the photon gets absorbed by electrons, and those electrons can then be extracted via external circuits like this one here and like this one here. And so that's the basic mechanism of how a solar cell works, and that's what we normally use in our labs. We measure solar cells in our labs on a daily basis. Okay, so let me introduce you to defects in perovskites and why they're important. This is very important for material scientists. I'm a material scientist, and I've been trying to understand how defects affect the properties of a material. And so one of the things that we always look at is the efficiency of different materials, the efficiency over time of different materials. So here's the power conversion efficiency of a solar cell, of 4 different types of solar cells since the 70s, and then all the way to basically a few years ago. You can see how gallium arsenide, crystalline silicon, cadmium telluride, and SIGs, these are 4 different types of technologies, have emerged over time. Crystalline silicon is the most commonly used material. So if you look at solar panels anywhere, that's going to be crystalline silicon. And it took a while for us to get to these very high efficiencies, right? So efficiencies of in the range of 25% only were achieved very recently, like 10 years ago. And gallium arsenide is a little bit different, but also that this is a very, very expensive technology, not normally used in satellites, for example. Crystalline silicon is more like what you see everywhere. Cadmium telluride is another technology that you see is about 5% of the market. So you see some of that also in the fields, but most of it is going to be crystalline silicon. Six is technology that is not very commercially viable. It's not really active in the market. And here's perovskites. Look at how fast perovskites went from not existing, which was 2011 or 12. This is when we started working on perovskites. And then in very, very short amount of time, this material became very close to, and actually now this is actually right around here. This is outdated data, but perovskites are basically as efficient as silicon. And it only took about 10 years for us to get there. So one of the things that we've been trying to answer is why. Why is it that this material has risen in efficiency so quickly compared to other technologies? And the reason why is because of point defects. I'm not sure if you know what point defects are, but I can, because of, that's a very material science term, point defects. But it's basically if you have a lattice of atoms, a bunch of atoms that normally, this is the perfect one, right? So we have here the organic sitting in the middle. We have the halide, the iodine, for example. Remember how we have Corner sharing everywhere? And here we have the lead. And when we have point defects, we actually have the absence of an atom, for example, in a vacancy, or we have an extra atom, like in an interstitial, or we have an anti-site substitution, where basically an atom is substituting an atom where it shouldn't be, or we have a Frankel defect, like this one here. Basically, the defect, the atom has moved location from the center all the way to the side. Schottky defects would basically have two vacancies next to each other. And then we have other things like impurities. So we can add impurities to, like, for example, let's say we add iron because there's a lot of iron everywhere in the processing. Then iron kind of sits there and it creates a defect. So all of these are defects. And so what does a defect do to the semiconductor? To most semiconductors, what it does is that it creates some states where the electron wants to go to die, basically. So an electron normally through light absorption, light comes in, excites the electron from from a low energy state, and it goes up in energy. And then when it goes up in energy, what happens is that we want to get this electron out into the circuit to power your bulb or to power your device. But instead, when we have these deep trap states, what happens is that the electron, instead of getting out into the external circuit, it goes into the state and we lose it. Basically, this state is like a dead end for the electron, and we lose that. So in most semiconductors, that's what happens when you have defects. You have defects that basically affect the number of electrons that you're taking out, or the electricity that you're taking out from your system. In halide perovskites, those defects give you what we call shallow states. That means that those states are very, very close to the place where the electron is. And at room temperature, those electrons go down in energy into this state and then go back up in energy, because there's enough thermal energy at room temperature that you have this process happening. So in general, what we know is that these shallow traps are benign. They're not bad for the device, and it allows us to extract these electrons. These electrons are able to then be extracted into the system. So that's basically what gives rise to these very impressive properties of perovskites compared to cadmium telluride. So here's the photoluminescence of a material, of two materials, perovskites and cadmium telluride. And you can see that they're pretty, actually perovskites are even better than cadmium telluride. And we're using very dirty processing to make this perovskite. So that means that we have a lot of defects. But they're not bothered by those defects. Perovskites don't really care about those defects. Cadmium telluride does. Cadmium telluride, if you have a defect, this is why we have this lower photoluminescence decay, or faster, let's say. So, so the reason why we think these perovskites have done so well over time is because there is some degree of defect tolerance, and that's led to these materials uh, being very tolerant to kind of dirty processing. All right, so in my talk, what I also want to highlight is the role of extended defects. This is more like, for example, if you have cracks in your film, or if you have a bunch of junk kind of sitting on the top of your film, things that we don't like crystal surfaces with dirty chemistries or grain boundaries, or for example, precipitates where we have a bunch of atoms that are sitting in one specific area of the material. And so my group has been doing a lot of work over the years to try to understand that. We use these very interesting probes at synchrotron lines in national labs that help us focus a beam, a very, very strong beam of X-rays. You can think of like the X-rays that you use for your for any medical application, but put that on steroids, and it's going to be really, really intense. In fact, if you are in the same place where that X-ray is, it will kill you instantly. So we don't want to be in there, and we actually have these huge chambers covered with lead plates that help us shield that X-ray from hitting our bodies when we're doing experiments at the synchrotron. And so what we do is we have a bunch of optical cavities that make us focus the beam into this very, very tiny spot. And so that's normally what we do for focusing an X-ray beam. And what that helps us do is get information about the chemistry, for example, of a device. So here is a solar cell that we make in our labs. And we're going to take a look at that little corner there with this X-ray beam. And so the first thing that we look is at the gold signal, because this is a gold patch that we make and we deposit on the device. And you can see here how we have that corner being deposited there. We deposited that and we can image it. So whatever that signal is, that's gold. And so that gives us an information of the chemistry as a function of a map. The next thing that we can do is we can connect the device and get a current output, because X-rays have a lot of energy. They excite electrons and generate whole pairs that basically give us a current. So we can do a correlative study between the current and the chemistry of the devices. So these are some of the maps that we can obtain from that. Here, for example, we're looking at the bromine and iodine in the material. We have a lot of iodine and some bromine, and this allows us to look at specific regions. So for example, here, this region is bromine poor. It's not homogeneous. There's a lot of heterogeneity. And that's bad for a solar cell. We want to make sure that we have homogeneous distribution of atoms across length scales. The next thing that we can do is, for example, look at rubidium. Rubidium is one of the inorganic cations, ASAT cations that we can put in the system. And you can see that they don't like to distribute very evenly. They form these kind of dendrites or structures that look like this. And what we can do is use that map and correlate it with the current. And you can see here that this signal here corresponds to this signal here. And so we can do correlative analysis of how different chemistries here affect the performance, the local performance of the device. More recently, we started to look into surface defects. We're interested in what happens when we have things at the surface and how does that affect the device. And so that's led us to start looking into what happens when you have these different chemistries. And these different chemistries are important at the surface because it helps us increase the voltage of the device. We want to go in this region here. So this is the x-axis is the voltage. In the y-axis is the calculated intensity of that voltage. Right now we are over here, but we want to be over here. And most of these laws, basically the difference between these two, is because we have a lot of defects at the surface. And so what we want to do is remove some of those defects, and we introduce materials at interfaces at the surfaces. But we don't know a lot about what's happening there, so we have three questions that we want to answer at that interface. So what structures do we have in that surface when we put some of these organic materials? How stable is that interface? And what is the mechanism by which this surface passivation happens? I'll try to answer these first two questions quite quickly in just a few slides, and then I'll spend a little bit more time on this one because this is the most interesting part. So for us to look at the surface, the structural surface of a material, we go to another synchrotron beam line. This is at Brookhaven National Lab in New York. We go to National Synchrotron Light Source, NSLS number 2, where we bombard again with X-rays our material, but at very, very shallow angles. So we have angles of 0.1 or 0.01 degrees, so really, really, really shallow. And that can only be done at really long distances. So we have this huge line, meters and meters and meters of length, where we shine the X-rays, and those X-rays then bounce off and create some signal. And that signal tells us something about the structure at the surface. And so, for example, for a control device, that means a material that only has the 3D perovskite on top. We have 4 rings, 1, 2, 3, and 4. So that's the structure that gives us the structure is a cubic structure of that material. But as we start putting materials on top of that at the surface, we create these additional phases. And these additional phases are based on an organic material that we're putting on top that is a 2D perovskite. Remember how I was talking about 2D perovskites at the beginning? So we're now forming a 2D perovskite on top of a 3D perovskite. This is a 3D perovskite. Over here is a 2D perovskite. And here are the signatures that prove that we have a 2D perovskite. And here are the signatures that prove that we have a 3D perovskite. And so that basically helps us understand what the structure is. We now know what structures we have at the surface thanks to this characterization tool. Now let's try to answer what happens when we have a when we stress these materials. We're going to put some heat in these materials. So let's put some heat. We put some 100 degrees Celsius for 10 minutes, and you can see that these features that were here now start to disappear or like fade away. They're still there, but they're starting to fade away. So that means that we're losing some of that material, some of that crystallinity. So the material is not very stable under heating conditions. And then after 40 minutes, holding it for the same amount of temperature, 100 degrees Celsius, those features almost entirely disappear. So these materials that we're putting on the surface originally are very crystalline and very stable, but as we heat them up, you can see here, those signals disappear and then almost entirely disappear over here. So, so this is the cartoon that we propose for this, that we actually have a 2D structure that forms on the surface. And then when we heat up the material 100 degrees for 40 minutes, this material kind of crumbles apart and starts to lose its crystallinity, which we don't want. So the materials are not very stable under heating. All right, the next question that I wanted to answer that I mentioned we want to study is what are the mechanisms by which surface passivation happens? And you know, people have been putting these molecules, forming these 2D structures on the 3D materials, but people don't understand exactly why they work better. So that the devices work better, but we don't know exactly why. And we have a hypothesis. We think that this has to do with phase transformations. Basically, I showed you before the structure, right? This is the corner sharing. We have corners here that are sharing those atoms. Those octahedra are sharing those atoms. And in the middle, we have formamidinium. Right here in the middle is formamidinium, this structure here. This little sphere here is formamidinium, is an organic molecule, but that organic molecule is a little bit too big. So it likes to be out, likes to have more space. So it's kind of forming, it's a little bit too big to be sitting here. And so what it does is it disrupts this structure, it cleaves it, and you have transformation into other phases. So for example, here, what happens is that we have now octahedra that are cleaving and forming these smaller structures, or in other cases we have some corner sharing and then no corner sharing here, for example. So there's a bunch of different phases that can form, and we call these hexagonal polytypes. And so what we wanted to do is test whether we can make those structures, but now in using synchrotron beamline, but now controlling the environment under which we do the measurement. So we introduce air, we introduce nitrogen, we introduce humidity. So for example, in a very humid day like today in Atlanta, we will have a lot of humidity. Does that affect your degradation, the composition of that material? And so we started with dry air, and pay attention to this peak here. This is the structural peak that tells us that we have a perovskite. And with dry air, that perovskite peak is pretty stable over time. So we're talking about minutes being exposed to dry air, nothing changes, right? So that's beautiful signal telling us that the perovskite is still there. And then as we go and introduce water, so this is water that is being introduced and with nitrogen as a gas. So this is not like your environmental conditions, but we wanted to remove oxygen from the equation. So having only water doesn't do much either, right? So we have the perovskite also pretty stable. Now what we will want to do is have water plus air. So basically moist air, right? So air plus water, and then we see this phase transformation. You can see here that we go from this perovskite layer, this perovskite structure into a non-perovskite structure. Basically, no corner sharing happening there. And that was a big discovery for us, because it told us that both air and moisture are needed to degrade the material. So we repeated that measurement. We went back again and said, okay, let's check that this is not a fluke. We did the same measurement. This is a similar sample, but at a different time, 3 months later, and you can see the same thing happening. But now what we've done different is that we've put this organic material at the surface. Now we've put this PAI structure, this organic material that forms that 2D structure on the surface. And in both cases, exposing them to moist air. And you can see that when we have this 2D structure on the surface, the perovskite doesn't degrade. And so this is what we think is happening with our system, that we are preventing the degradation when we put these materials on the surface. So the surface plays a role, but it might not necessarily be that it's passivating electronically, but it's just protecting your sample from degradation. So from that, we wanted to actually go and look at how we can use that interface to understand phase transformations in other processes. And in this case, the vapor phase. So we deposit all the stuff that I've been showing you so far is perovskites that we deposit from a solution process. We dissolve chemicals, we kind of smear them on top of a piece of glass, and then we do tests on that. But we also have, especially because industry is interested in the vapor phase, we wanted to understand whether we can control phase transformations, basically the structure from the vapor phase. So what have we learned from the interface and its effect on phase transformations? So here's the chamber that we use. We have this big chamber that is sitting in our labs. And we have 2 different precursors that we can control the temperature of and evaporate it. Here you can see this cone here. This cone here is basically we evaporate the material. The material goes and is in a vacuum chamber, and it gets deposited on the substrate. And then the FAI, the organic material, gets also deposited in this plume. And then you see that this goes and interacts here. We co-evaporate them. So we evaporate them both at the same time, and we form a film over time. And when we do this, what happens is that we actually don't have, we don't form the phase that we want. We want to form a perovskite phase, which is this peak here. It should be a peak around 14 degrees. But actually, we form some polymorph, some other thing that is right here. And so we were very disappointed because we thought, okay, it seems like we cannot grow these materials. And even after we anneal those materials or subject them to heating, that peak, instead of becoming smaller and growing the 14-degree peak that should be here, that peak actually becomes larger. So this is not what we want. So we went and decided that we wanted to look at surface chemistry. So using the surface as a way to help the growth of these materials. And we use these two molecules that we put on the substrate. So what we do is we spin coat, or we smear a material on the substrate, on the glass. We spin coat it, smear it, basically a very, very, very thin film, and then we anneal it. So then we have these molecules kind of standing right here, right? So these molecules start to arrange themselves, and then we deposit the material. And so with those molecules, we were able to find the 14-degree peak. So these molecules, this surface, helped us grow the material that we wanted. And we have a proposed mechanism that basically we know there's an interaction between the molecules that we're evaporating on the material and some of these molecules that we have on the substrate. If you look at the stability of this material, they are pretty stable. So we're basically subjecting them to really high moisture content, close to 100%. And you can see that the materials degrade. Some of them degrade faster than others. The vapor processed with the organic molecules are much more stable than without any of the material. Any of the molecules. All right, so with that, let me conclude, because I know that this is a lot of material science to discuss in 40 minutes. So I'm going to conclude here. And my conclusions are that we're very interested in the interface and how those interfaces enable the phases, which then help us make a better or worse solar cell. So here, for example, we've seen that adding this organic molecule on the surface helps us prevent phase transformation. So more stable material. We've also seen that when we have this phosphonic acid molecules, we have the cubic phase, which is what we want. So we're able to control the structure of the material by modifying the interfaces. And the thing that I always like to end up my talks with is an image of an atomic, you can see atoms here. All these little dots that you see here, all those little dots, those are silicon atoms. And we deposit on top of those silicon atoms, we deposit these layers. You can see those lines kind of going that up top to bottom like that. Those layers are atoms of lead and iodine that we deposit by a process called ALD, atomic layer deposition. So we do a lot of characterization like that at Georgia Tech, a lot of deposition that has atomic control. And we're very interested in learning more about how the atoms, the atomic arrangements leads to different properties in the materials. And with that, I would like to thank you guys for your attention, everybody here, and also your everybody who invited me for this. I'm really happy that we get to talk a little bit of science, and happy to answer any questions.